Okay, let's look at another couple examples of double integrals. These two questions, though written slightly different, are actually asking the same thing. Now, I started to put a little sketch for each of these here. This one goes here, this one is here. I didn't finish it because I can't draw in 3D as most of us, especially if you're asking me to graph this function z equals xy squared right here. I don't really know what that looks like. But what I wanted to point out is in 3 dimensions, typically we kind of draw xy like this, and here's the flat space here, right? X is from 0 to 2. Oop, and I only went from 1 to 2, so this actually comes over a little bit more. Okay, because x ranges from 0 to 2, so from here to here, right? But y ranges from 2 to 3, so it's projected onto this surface here. But the thing we don't know is what shape that function makes. So whatever xy squared looks like, it protrudes up, right, and has some sort of curves. I don't really know. I'm just faking a drawing there, like I know what it looks like, but I have no idea. So when we double integrate this, the bounds from 0 to 2 for x, and then the bounds from 2 to 3 for y, that's what we're going to use over here in our integral. That's our r. Looking at the second one, really the same thing. They don't give us the double integral, but they tell us these bounds. X goes from 1 to 3, y goes from 0 to 1. And then this is our height function here. That's our z, x squared plus y squared. Okay, so again, this thing protrudes up and it does something. My guess on this one is some sort of hemisphere, only because x squared plus y squared is a circle, but I don't know. It really doesn't matter. When we double integrate, what we're doing is we're calculating the area one way, and then we calculate the area the other way, and that double integral ends up building this height here. All right, so let's do the math. The math is much simpler than what it looks here. Okay, we don't even need to worry about this shape. So we have xy squared. Notice dx is the inner function, right? dx. Well, that means then that this integral, the inner one, should be from 0 to 2 because that's our x here. Okay? And then when we do dy, that ranges from 2 to 3. So this outer integral, 2 to 3. Okay. Now I'm doing it this way because that's the way it is written here. Okay, they set it up dx dy, so we'll go ahead and do it dx dy. As long as that integral 0 to 2 stays with the dx, and the integral 2 to 3 stays with the dy, it really doesn't matter. If these range from some variables, if the bounds range from variables instead of numbers, it wouldn't matter. We need to do the variables first, so our answer doesn't end in variables. That would be kind of weird, right? Like, what is the volume? The volume is 27x. Like, that doesn't make sense. Okay, so integrate this with respect to x from 0 to 2. So we have x squared over 2 multiplied y squared is a constant, right? So I'm going to leave that out front from 0 to 2. And I'll go ahead and just write, I just noticed, I don't know why I did that backwards, but this ranges from 2 to 3, not 3 to 2. If we did 3 to 2, we'd have to make it negative. So 2 to 3, lower bound, upper bound. Okay, I'm only focused on this x squared because the y squared over 2, right, I could just pull that out front, or even 1/2 y squared. So the x squared, I have 2 squared minus 0 squared, which is 4. So 4 times y squared over 2, right, that's just 2y squared. Now we integrate with respect to y. That's y to the third over 3. We still have the 2 up front. 2, 3. So I could, again, just take that 2/3 out. Let's save it for then. And do 3 to the third minus 2 to the third. So that's 27 minus 8 is 19. 19 multiplied by 2 is 38 over 3. What is weird about all of these problems is they're not giving us units, right? Sometimes math, they do that. I wouldn't need to know if it's inches or centimeters, whatever units I'm in, but it's a cubic unit, right? Because we did volume. A double integral produces, it calculates volume.